Now, in the last class, we were discussing about errors and uncertainties, specifically about errors. We discussed what thematic and random errors are and how they come into existence, and then how do they affect accuracy and precision. We did some examples for that. So today we will be starting this, uncertainty. Actually, errors produce doubts. Higher and lower or lowest limits of doubt are called uncertainty. Like how much doubt we have, how much uncertain in something's value we are. That would be known as uncertainty. So in simple words, error is qualitative and doubt is the same quantity but study as quantitative thing. So quantitative study of the thing is doubt or uncertainty, and qualitative study of the same thing is errors. So let's start studying uncertainty. Now, the first one is absolute uncertainty. Absolute uncertainty has same unit as quantity. Absolute uncertainty has only one significant figure, and absolute uncertainty controls number of significant figures in measured or calculated. So very important thing is that absolute uncertainty has to have the same unit as the quantity measured, and it has to have only one significant figure. Let me tell you what does this mean. For example, if we measure a length and we find out that it is 13.5 centimeter with an uncertainty of 0.1 centimeter. So what does this mean? Actually, the length measured is 13.5 centimeter. But there is a doubt of 0.1 centimeter, that is 1 millimeter. So when we write its uncertainty, and what do you see over here? Plus, minus. What does that mean? It means it can be a plus, like the maximum value can be 13.6, or it can be a minus, that means that it can be 13.4. So the value of length can be any number from 13.4 to 13.5 in between. So this is our doubt or absolute uncertainty. Note: with calculations, uncertainties always increase when we calculate a quantity using two or more quantities. Every quantity has its uncertainty, and when uncertainties mix together, we have more uncertainty. So try to understand that whatever we calculate, with calculations, uncertainties always increase when we mix together many quantities. So here are some rules for absolute uncertainty. For addition and subtraction, when we add or subtract quantities, their absolute uncertainties are added. So this is very important for you to see over here. When we add or subtract quantities, their absolute uncertainties are always added.
Added.
Now, what does that mean? See, if we have x equals to a plus minus a, and we have y equals to b plus minus small b. So these are two quantities. I'm not giving you any numbers. I'm just giving you alphabets. Okay. So that means that this will generalize our calculation. How do we find? Now, in case of x plus y, what we have to do is we have to add a and b to find what x plus y is. But for its uncertainty, we will be adding a's uncertainty and b's uncertainty. Okay. So this is rule number one. Rule number two, if we have to do x minus y, then we simply subtract b from a to find what x minus y is. But to find uncertainty, we again have to add the uncertainties. So no matter we plus or we minus, we always add the absolute uncertainties. Okay. And this is for addition and subtraction. Now, fractional uncertainty. A very misleading question that a teacher can ask in a class is that if we measure something, if we measure length of something and we get an uncertainty of 0.1 millimeter, that means 1/10 of a millimeter. Okay. So is that uncertainty a large uncertainty or a small uncertainty? Normally what happens is when students think of a millimeter, which is very small, and then they start thinking 1/10 of that small millimeter, they say it is very, very small. So it means somebody is making a very small uncertainty. So they tend to, most of the students, they tend to say that it is a very small uncertainty. But it is a trick question. Actually, we cannot tell. For example, if somebody asked me that I was measuring something and I made an uncertainty of 0.1 millimeter, is that a big uncertainty or small uncertainty? I would say what you are measuring. What was the quantity that you measured? If the quantity that you measured was a very big quantity, for example, length of a table and height of a person, or you were measuring, for example, length of a, a pet bottle or something. So in that case, your 0.1 millimeter error is a very small error. But for example, if you are measuring diameter of an electric wire, which is only 0.5 millimeter, if you are measuring diameter of an electric wire, then 0.1 millimeter error is a large error. So this is point for you to think that the same error can be a large error or a small error. So how would we know? So there comes a way of knowing how big an error is, and that is called fractional uncertainty. What is fractional uncertainty? It is absolute uncertainty divided by quantity measured or calculated. Okay. Now, fractional uncertainty is absolute uncertainty divided by quantity measure. For example, if you need a fractional uncertainty of x, then it has to be a divided by capital A. Fractional uncertainty of b, small b divided by capital B. So fractional uncertainty is absolute uncertainty divided by measured quantity. And when we have done fractional uncertainty, this is the time to do percentage uncertainty. Percentage uncertainty equals to fractional uncertainty multiplied by 100. Percentage uncertainty equals to absolute uncertainty divided by quantity measured or calculated multiplied by 100. Okay. So this is how we can find out percentage uncertainty. So we have two kinds of uncertainties now, fractional uncertainty and percentage uncertainty, other than absolute uncertainty. Now, let's keep going forward and let's see if these uncertainties come very effective. If quantities are multiplied and or divided, the sum of their fractional or percentage uncertainty uncertainties is equal to fractional or percentage uncertainty of their product. If multiple quantities are multiplied or divided and they produce a product, the fractional uncertainty of the product is actually the sum of fractional uncertainties of all the factors. So let's see. Mm, If z equals to w multiplied by x divided by y, where w equals to c plus minus c, x was equals to a plus minus a, y was equals to b plus minus b. Now, rules are rules. Number one, fractional uncertainty of product equals to sum of fractional uncertainties of factors. And same rule can be extended to percent, because percentage and fractional uncertainties are same. Every fractional uncertainty is multiplied by 100, so they change in the same ratio. Hmm, Percentage uncertainty of product equals to sum of percentage uncertainties of factors. Let's see how we can apply this to the above case. Fractional uncertainty of z equals to fractional uncertainty of w plus fractional uncertainty of x plus fractional uncertainty of y. So let's slow down. Let's see what did we do. For example, if z is a product of w, x, and y, regardless if one is dividing or multiplying, we always add their fractional error. And the sum of the fractional error is not making absolute error of z. It is also making fractional error of z. For example, you did not know z and you did not know the uncertainty in z. So what you can do, first step, just put the average values of w, x, and y, like a, b, and c, capital values, into the formula and get the value of z. That should be your first step. Now, if you have value of z and let absolute uncertainty of z equals to x, then it will be x divided by measured quantity of z equals to fractional uncertainty of w. That will be c over capital C, plus of x will be a over a plus b over b. You know this, 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 and you have already calculated z. So all the ticked quantities are there that you know. Only x is what you have to calculate. So you put everything in formula, you put all these values in your calculator in one go, and then you multiply the answer with the calculated value of z, and you get the required uncertainty. So this is a very common question. Examiner is very fond of this thing. This is an FAQ, frequently asked question by the examiner. And this is how we can do it. And one more thing. What if there would be some powers on x and y? For example, if there would be square on x and cube on y. Actually, you should not be surprised. It means w into x divided by y into y into y. So what should happen is there should be a over a and other a over a, because there's another x multiplying over there. And b over b plus b over b plus b over b, because there are three y's multiplying over there. Or if we are smart, what we can do is we can multiply this b over b thing with 3 and a over a thing with 2. And this should also solve the problem for us. So this is a very common question. And one more thing. Examiner will give you a formula. Most probably, you might not be familiar with it. Like 90% of the times, the formula that examiner gives you are not familiar with that. Okay, either he makes the whole formula or he asks you to make a formula, and that would be a totally new formula and most probably not part of your syllabus. So examiner wants to see whether you can apply the knowledge of these uncertainties on an unknown situation or a new situation or not. So I'm using a formula from the syllabus, but for you right now, I consider that formula to be unknown. And this is Young's modulus, E equals to 4FL over pi d square x. In this formula, E is Young's modulus, F is force applied, L is unstretched length of wire, D is diameter, X is extension. And data given is that F equals to 12.5 plus minus 0.1 Newton. L is 1.45 plus minus 0.01 meter. Diameter of the wire is 0.55 plus minus 0.02 millimeter. Extension produces 1.11 plus minus 0.01 millimeter. We have to calculate E and its uncertainty. Now, who is up for the job? Who thinks that he or she can calculate it? Let's give it a try. Take a screenshot of the board right now. Can you do that? All of you? And let me know when you all have done it. Okay. Now